right, that's showing step-to-step engineering. You apply the two functions, you get efficient result. You get also in your process data, you get information, impedance protection trip or distance protection trip. You know exactly what is going on everywhere. All right, that brings us really to, I think, our final topic that we want to talk about today or this morning is teleprotection. The teleprotection is a very effective supplement or add-on to the distance protection. What can we see here? We can see here normal line, and as we saw this morning, the zone 1, typically 80%. That means you've got that safety margin over there, B, and a safety margin A from the other side. Both of those are about 20%. So if you look at the total line length, those two shaded areas sum up to 40%, almost half the line. So if you assume your line faults, purely statistically, almost half the faults you will have will be either in A or in B, if your faults can be anywhere. That means half the faults you have on your line are not tripped instantaneously, because for the fault at B, we will have a zone 2 trip on the A side, and for the fault at A, in that shaded area, we will have a trip in zone 2 from the B side. It means the fault from either side, one of the sides will be delayed tripping, we can call it that. And delayed tripping is not good for power quality, system stability, and the many things. We want to try and avoid that, and the teleprotection will give us a technique to do that. Again, now in the Dixie project tree, you can see there are a number of teleprotection schemes. You can see the teleprotection scheme, distance protection is 25, 85, 21 are your distance protection teleprotection schemes. You get a blocking scheme, reverse interlocking scheme, permissive overreach, permissive underreach, 4 different schemes. The reverse interlocking scheme is added here. That's what we spoke about just now when we did the transform protection. Remember, for the LV bus bar, the 20 kV bus bar, the zone 1 with the reverse interlocking from the feeders. That's this scheme over here. It's applied as a teleprotection scheme because essentially you have the zone 1, which is controlled by the feeder with reverse interlock signal. So it's an external signal you couple into your distance protection. We call it teleprotection. Not going to be considered here. The schemes we consider here are for normal feeders, and for those we have the blocking, permissive overreach, permissive underreach. What you also see is 67N, the directional ground fault. Directional ground fault can also be applied with a directional scheme, and the combination of the directional ground and the distance protection can be very, very effective. Especially, we spoke about it this morning, fault resistance. At some point, the fault resistance, if it's a high resistance fault, and that's why we sometimes refer to 67N as a high resistance fault protection or high ground fault resistance protection, then it goes beyond what the distance protection should be set to. Remember, we don't want to set the zone, the resistance reach of the distance zone too big. Remember, the symmetry requirements, X to R and so on, are limited. If you run into difficulties with the R to X of a distance protection, don't try and overstretch this. Say, okay, I accept the boundary for the distance protection and I use the 67N to take over for the resistance, because it is very, very effective for the high resistance ground faults, also with the teleprotection scheme. And at the bottom, weak in feed. Obviously, as I spoke about it in the renewables, for example, I said will typically be weak in feed. You get also other weak in feed conditions. And with the teleprotection, you combine a weak in feed logic, which will improve your tripping speed overall on both sides. So you can get, even at the weak in feed side, a fast fault clearance to remove the system. I wonder, did I do 2 slides now? No, it was just a... All right, the 4 schemes that we are typically looking at with distance protection: PUTT, permissive underreach transfer trip; POTT, permissive overreach transfer trip. Then we have a blocking scheme and the unblocking. The unblocking scheme, I want to initially already kind of take care of that. That is really not a blocking scheme. It is more a pot scheme essentially, but it uses a special carrier situation that you have a monitoring channel on your communication system. It is a special way of using the communication system. That's why I want to leave that a little bit aside. The 3 schemes we're really looking at initially are the put, pot, and blocking. Starting with the blocking scheme. The blocking scheme, as you can see in the title here, talks about AM carrier. It is not restricted to that, but it's giving a little bit the background. Why do we use a blocking scheme, and what is a key situation where you could say the blocking scheme is important to me, I want to use it, and it depends on your communication. And the important thing is, if you use a blocking scheme, if you have an internal fault, remember that's the definition of the blocking scheme. When the fault is internal and you want to trip, you are not requiring communication. That means if your communication system has difficulty to get the signal through a fault, remember sometimes the communication goes on the power line, like the power line carrier. So you can see the AM carrier referred to here. And you need to get the signal through. This signal might have difficulty getting through a faulted line. So if the line is healthy, then the blocking scheme would communicate, and you can be sure the signal will go through, because it's only sending a signal when the fault is external. And then the line is healthy, and the blocking signal can go through a healthy line and be received and blocked, and everything is stable. So the point is, the blocking scheme is essentially applied where you have got difficulty, or you cannot be sure that your communication system will work if the internal fault is there. Then you simply say, all right, I don't care if the fault is internal, I don't need a signal, so I'm going to trip. I only want to be stable on external faults, so I need a healthy line to send a blocking signal through a healthy line. That is a little bit the history there. The put is simple. There we use an underreaching zone to send the advantage. You can see at the top there, used for longer lines. Why not on short lines? Because definition of put scheme, you are using an underreaching zone. What is the underreaching zone? It's zone 1. Zone 1 is used to send. What is the problem with zone 1? On short lines, the X setting is small, and due to our X to R ratio, the R setting is also small. We don't get a secure resistance reach on short lines, not with the zone 1. Remember, there's a situation of tower fitting resistance, the weekend feed, and so on and so on. It's not very dependable on short lines. That's why you can see the put scheme is not good. Middle length lines, long lines, where you've got a fairly good zone 1 setting, you can have a good resistance reach. It's extremely simple because you only send when you have tripped. All right, so I've looked at these schemes, blocking and put, say that they come if you have certain external compromises. And in the middle, we've got the pot scheme. The pot scheme always works. Okay. If you assume your carrier will get through a faulted line, obviously, that's why you can see using special frequency shift modern carriers. The AM carrier is an older type of carrier system, not used nowadays at all, I don't think anymore. Very cheap. Well, not cheap, it's just older, all right? But the frequency shift carrier, you can be dependable that you will get through the fault. Also, if you couple the carrier onto 2 phases, gives you a better coupling of your carrier signal to the line. You will get a dependable signal through the line. Even if it's faulted, it will work on short lines. Why? Because you're using an overreaching zone to send. You will send also on external faults. And then you can see the problem is going to be you are going a more complex system, because the receiving end will get a release signal even on external fault. It needs additional logic. And you get into transient reversal conditions where it can be complex. And so you need some additional logic, a more complex current reversal guard logic for the pot scheme. So that's really summarizing it. Put, extremely simple. Short lines is difficulty. Blocking, you get slightly slower tripping always, but it works even if your carrier system is very poor. Pot scheme works everywhere, but is more complicated. Okay, that's what one should just consider. So there's just a little logic diagram of this. I don't want to spend too much time on this. You can see here, this is a put scheme. Zone 1, your underreaching zone, is applied here. It's the one that's going to transmit the signal. And if you receive the signal over here, you would simply use an overreach. You'd release an overreaching zone to trip immediately. Basically, it's just simply very, very simple. You could almost take the received signal and trip directly. You don't do this because there is always a risk of a mistake by the communication. If the communication sends you an unwanted command, so just by accident, and there are some probabilities statistically, I don't know whether 10 to the minus 4 or 5 is the probability. So if you've got 10,000 power line carrier systems, you'll get about 1 unwanted command per year or something like that. If it then directly trips, that would not be good, even if it's only happening once a year. So you put that received signal into a zone 1 overreaching zone release, and that means that the chances of that unwanted command coming from one of your 10,000 relays once per year and a zone overreaching zone pickup at the same time, that is not 6. That's if you're going to win the lottery 3 weeks in a row, effectively. All right, the pot scheme looks almost the same, only is that we are now using an overreaching zone to send, right? And you can see with the receive signal, the release is the same. Again, the receive signal would release your directional overreaching zone. So it is like a direction comparison. If you have an internal fault, then both sides, zone 1B will pick up. The one side sends, the other side sends. They're both sending, both receiving, and they have a pickup forward. It's a trip. If the fault is reverse, over here, the remote sides would see it and zone 1B would send. The local side would not see it in its forward zone, would not trip, okay? But the local side would not send, but it's reverse. So only one side sends here, and the receiving side will not see the fault in its zone 1B and no trip. So the system is stable. Also, it's a direction comparison scheme effect, not exactly, but almost. Blocking scheme is a little bit different. Here you can see there's some logic over here. Pick up forward would block it. You can see, be careful here. See pick up forward, but it goes in inverting input, so it's going to block the send. So you have a pickup wants to send, but if it's a forward pickup, you will not send through the AND gate. It's blocked. So you will only send any pickup, so very sensitive, but not forward. So every reverse fault you see, you will send a blocking signal. And on the remote side, when you receive the blocking signal over here, you're going to go in and prevent the tripping. So sorry, here you see the receive signal comes here, inverts the input to the AND gate, and the AND gate is blocked. You cannot trip. You need some time. Now the problem is when you get the pickup and you immediately want to trip, that would be too soon. You have to wait for the receive signal. And that's where you have this coordination time here. You are waiting. That's the T. You're waiting. It's the channel delay time, some safety margin to wait for to give the remote side to send you the block signal. If you don't have the block signal when this timer here expires, the permissive scheme will trip. And then you see at the top here an add-on which is not classic blocking scheme. It's an option that you can apply together with a blocking scheme called so-called jump blocking. The jump blocking will send immediately at fault inception. That is extremely fast, about maybe 15 milliseconds faster than normal pickup, but it comes on a sampled value immediately. It does not have to filter out anything. It comes on the delta at the fault inception. You can see the delta. So it's approximately 15 milliseconds faster than the pickup here. That can send immediately, but it's not directional. It's just saying send immediately. And then that way you would get the receive here very quickly. You get the receive if the channel delay is 15 milliseconds, you get the receive here at the same time as the pickup. That means you could, in theory, change this time TV to 0, approximately. Because your jump blocking will be here when you get the pickup. Normally you can reduce the time. I wouldn't necessarily set it to 0, depending on how fast your channel is, but you can reduce it. And the technique is like this, that if the fault is reversed then this blocking here would be taken over by this blocking and the blocking signal continues and you won't trip. If the fault, however, is forward, the forward detection, you can see here, will reset the jump. Immediately, as soon as you see forward, you take away the jump block send. That means that the other side, the receive signal will be taken off. And as soon as the receive signal drops out, you can then trip. So it is just an add-on to make it possible to set this timer a little bit shorter. You don't need it, but can be used. The unblocking scheme, remember, it's the final one I said, is not a blocking scheme, it's an unblocking scheme. It is actually a permissive overreach scheme, but it uses 2 carriers. You can see it's FU and F0. The F0 is a monitoring signal which is sent all the time. It's written as F0 and FU because it's typically done with a frequency shift carrier. It means you've got your 0. F0 is a frequency which is your monitoring or blocking frequency. As long as you receive F0, the received block is happy, says the channel is healthy, is ready. If the F0 disappears, it's going to say, ooh, okay, it could be a fault. It'll have a certain time. If the unblocked receiver is then received, then it'll say, okay, I have dropped out F0, I've picked up FU, I will release and can release the tripping, essentially like a pot scheme. If however the F0 disappears and FU does not come, then there's a certain timer here, and say timer will say, oops, somehow the carrier has failed, the communication has gone away. The F0 has disappeared, I'm receiving nothing, I'm not receiving FU or F0 channel failure, it'll give you a channel failure alarm, and the logic will deal with the communication failure. That's just a different technique of doing it. That is different receive block as such. The teleprotection can be phase segregated. This is a big advantage in some applications. It's sometimes also forgotten. Here we see a double circuit line, and we did have the question this morning about the 4 lines on one tower and so on, and we said obviously the mutual coupling and so on is very, very difficult to consider there. We have to set a smaller zone 1, and in these applications, double circuit lines, your dependency on the teleprotection is higher. Right, to get secure trim, because you would probably have to set your zone 1 smaller to make allowance for the influence of parallel line coupling. So the teleprotection is extremely important here, and the other thing that can happen on these double circuit or multi-circuit lines, you get inter-system faults. Okay, and for this example we've shown it's the same voltage potential, maybe they were actually coupled on both sides as well, and you get a fault, A ground on the one tower and B ground on the other tower. It's probably maybe an inter-system fault that they are flashing over to the tower, and the arc on the tower burns into the other line. So you get this. Normally, if these were 2 independent lines, not on the same tower, the chances of a fault A ground, B ground happening simultaneously is very, very small, very remote. But if it's the same tower, meaning it's 2 circuits on one tower, then this type of fault is not so remote, can happen. And we want to get phase selective single pole tripping on both feeders, because if we trip both feeders 3-pole, that would be really, really a bad interruption of the system, because we would maybe lose complete interconnection of the 2 stations. If we get a single pole trip on both feeders, then the 2 stations are still strongly connected. You can get a lot of power transfer between the 2 stations. They will remain synchronous. The stability is much, much improved. All right, how can one do this? You can see on this side, if it's all coupled on both sides, then there will be a pickup here, zone 2, AB ground. These 2 relays would pick up face to face to ground and would want to trip 3-pole inside there, zone 2, because it's a remote fault. All right. These 2 sides would see A ground and B ground single phase forward, zone 1 trip, and then if you use a teleprotection, either put could be used here because the zone 1 pickup, or also a pot. As such, these remote sides would send a phase segregated signal, they'd send us, say this one would send a B release and he would send an A release. And on the receiving side, they would say, although I have a pickup AB ground, I only get a release for A, so I would trip single phase. So you can get single pole tripping at both sides for this condition here. And that's, as I say, is done in the logic independently. You can do this with binary inputs, or as we'll see later on, with the built-in serial communication. So you have a choice. You can do this phase selective tripping with binary inputs or with a protection interface. A protection interface is the serial interface in the relay. This could also be an Ethernet interface nowadays. For a couple, was almost more than a year now already. You have the BD module. You can put the like the protection interface over IP. Use a BD Ethernet module to get the communication, but that's a different subject. Okay, so the way in which your protection interface is configured doesn't really matter. That's an internal serial or IP interface to the remote end, and you can put your signals through this interface, or you can put the signals through contacts and binary inputs in the classic sense. Both of those can be phase selective, as you can see here. The binary inputs there, you can see there's receive ABC, you define each one independently, and further up there would be send signals also individually, ABC send, which you can route independently. If you use a PI, it will automatically be phase selective. So in the PI protection interface, you don't have to set anything special to be phase selective. It is automatically phase selective, the PI interface. Transient blocking, all right, that's a nice subject here, which one can talk about for a while. It is important for the permissive overreach scheme, all right? In the permissive overreach scheme, remember we said we have the condition that we will be sending on the external fault. So here I've taken an example. At the top, for example, you can see here 2 feeders again. Does not have to be a double circuit here, but here again on the double circuit, this is amplified, or this problem is more probable because of the mutual coupling, what we talked about earlier on, that during the second condition here at the bottom, the mutual coupling will pull this fault closer to the relay location, but that's just something else one can talk about, a bit technical. But on a simple level, the transient blocking is important, that the relay here remains stable, the top feeder remains stable and does not trip during this reverse fault, even though this reverse fault for the top feeder is going to be cleared sequentially. That breaker remains in while this one trips. Let's go through it step by step. So initially we have the top condition and we apply the fault here. And then I think there are some diagrams. No, they won't. I have to go through it one by one. Sorry. So what happens here initially, we will have a pickup on the right hand side reverse, and on the other side we'll have the zone 2B ground. So the left hand side at the top will be sending a signal. Here we will be receiving the signal, right? And this side at the bottom we'll see the fault here outside zone 1 but inside zone 1, so maybe the teleprotection is not working so quickly, and then we go over to this condition trip, and now things reverse. So you get a reversal here, that now over here the zone 2 is going to reset, stop sending. Over here you could get a zone 2 pickup and send. Now you can say, all right, why should this zone 2 pick up for the fault all the way down here? It's, as I said, sometimes you can consider a mutual coupling, because if you've got the fault current flowing in opposite directions, the zero sequence current, the mutual coupling will pull the fault closer, okay? And it could be that you've got a larger zone 2 setting to make allowance for other difficulties you have. So it's not impossible that the zone 2 would pick up once this breaker opens here. Now remember, from the top here, this side was sending a signal, and when this reset happens, it will stop sending, but this is a channel turnaround delay. The received signal could still be present when we change to zone 2 pickup here. And remember, zone 2 pickup and receive would be trip. We would trip this breaker on that condition. For that purpose, you need the transient blocking. And the transient blocking is really very, very simple. It's this relay over here which will activate it. It'll see the reverse fault. You have a setting over here. The first timer, the block pickup delay, that timer there, the 105 timer, and the number of it. You can see there, if you have a pickup that is not forward, or a pickup that is backup, that's an OR gate as such, and you have a general distance pickup at the bottom, those 3 inputs you see over there on the logic. Distance pickup not forward, distance pickup backward, or distance pickup backup, and a distance pickup. Those 3 conditions give you the input to the timer. And if the time delay is exceeded, then you would expect that must be a reverse fault. And the time delay you set on the pickup delay is the typical breaker time here. So you're saying, I'm seeing a reverse fault. I'm expecting this breaker here at the bottom to trip. So I'm just going to wait the time of the breaker, and then I'm saying, if I've seen it for that duration, typically about 20 milliseconds, then I will be sure that there's definitely a reverse fault, not something transient, and I will activate the transient blocking. If now this breaker really does trip, then the transient blocking is active and it will not drop out instantaneously. You have a block hold delay, which is typically set to around about the channel delay times 2, typically about 50 milliseconds you set here. So for a further 50 milliseconds, you'll keep the transient blocking active. And that means even though you have a zone 2 pickup now, and you may still have a receive which has not yet reset, you will not trip with the pot scheme because the transient blocking prevents it. And you will also not send a signal. That's the other interesting, you will also not send a signal. But normally here the zone 2 pickup will send a signal, but the zone 2 pickup with the active transient blocking, there will be no send signal. It's really sounds more complicated than it is. It's really fairly straightforward. One other aspect we still need to look at quickly is the weak-in feed. The weak-in feed really is 2 aspects. The one is the echo and the other one is the trip. The echo is clear that if you have a weak-in feed condition, you want to tell the strong-in feed, look, I'm not seeing the fault, but it's definitely not reverse or anything, so I'm going to send you an echo and you can trip. The weak-in feed tripping is again more secure. Again, because of remember the unwanted command, if for some reason the remote side sends a signal and there's not really any fault or anything, it is just an unwanted command that the communication equipment did by mistake. We don't want to trip on that. We will check the voltage criteria. You can see there's an undervoltage check. So if that unwanted command is received and you have an undervoltage, then in theory you could trip with weak in feed, but that should normally not happen. Normally, if the system is healthy, you will not have an undervoltage. All right, I think there are small logic diagram for that. I think that's from the manual. I don't want to go through this in too much detail, but you can see at the top, there's basically going to be an echo release over here, which is coming from the distance protection and weak in feed. There's a certain logic saying you must have a distance protection there. If the distance protection is switched off or the settings, there is no distance protection, you cannot get an echo release. So if the distance protection is blocked due to emergency mode, and you have an emergency mode, then the emergency mode can replace the distance protection. So that's done internally. You don't have to, there's no settings required for that. It's done in the internal logic. If, however, you get basically a weak in feed condition, but you have a received signal and everything is healthy and there is no pickup, then you would say, all right, I'm getting a received signal, I have no pickup. So for me, it looks like I'm a weak in feed because you are receiving, and you would then release the echo, and the echo would then be sent here. There are some stabilizing techniques here to prevent ping pong echoes, that the system locks itself up, that the one guy receives an echo and then you send it back. There's this timer which says if I have sent a signal, I cannot send an echo shortly afterwards, otherwise you get the system locking up. That's all done internally with the default timers. So essentially, if you have the no pickup and a receive, you can see that on the left hand side there, there's a receive for echo going in there, then there's no pickup, distant or emergency protection, no pickup, then that'll release the echo, and the echo release, if the timing here says there was no send signal, I didn't send a signal, so I'm not echoing my echo, and so on, then it'll release an echo signal out here to allow the tripping. The thing that we must worry about if we're going to apply the pot together with some weak in feed is that our zones are set correctly. And we must have a reverse reach. And this is a standard teleprotection scheme, whether you're talking about blocking schemes or weak in feed schemes or echo schemes. You must have the reverse reach, which covers the remote forward reach. And you can see this green area is correct, because the local relay here has got a reverse reach that goes up to here, this point here. And that reverse reach here is larger than the remote side forward reach. The remote side forward reach only goes up to here, and the reverse reach for this side goes up to here. So you have a good coordination. That is correct. On the other side, it's incorrect, because you can see the reverse reach of the A is too small. The B side at the bottom here, this B side reaches all the way, you can see, to the complete left. The pickup there, there is this pickup B forward on the remote or left hand side. It goes further than the A side reverse reach. That's why that red area is not big enough. That red area, the reverse reach must exceed the remote forward reach. And it's important because if you receive a signal, then you must, and it's a reverse fault, then you must see at least the same distance reverse as the remote side sees forward.